Our big idea is to find the area between two curves. Now I want to do that by looking at the area in a vertical fashion. Just to refresh our memory, if we wanted to find the area of the region under the curve y equals x squared plus 21 that's bound by the x-axis on the interval from -7 to +10. Initially, we estimated that area using Riemann sums, but then we moved on to using the definite integral. And to help us set up that definite integral is we used a representative rectangle. This rectangle would represent all of the various rectangles we used in finding our Riemann sum, and when there were infinitely many of them, then it became our definite integral. Now, when we tried to find the area of this representative rectangle, we recognized that the base was on the x-axis, and we called that the change in x. The height of this rectangle just ended up being the functional value of the curve at any point x. And then from these two pieces of information, we were able to come up with our definite integral of x squared plus 21. That delta x turned into the differential dx, and our limits of integration were just the ends of our interval, so from -7 to +10. From there, we would go on to evaluate the integral. So 1/3 x cubed plus 21x evaluated from -7 to 10. And you plug everything in, simplify it, and get the 804 2/3. I want to take that same approach when we're trying to find the area between two curves. Now, if I still have that same parabola, y equals x squared plus 21, but we want to find the area between that curve and the line y equals -x minus 7, we're still going to use a representative rectangle. The base of that rectangle, because it's a horizontal distance, is still going to be the change in x. It's just that the height of our rectangle is no longer just the functional value of the curve, because we need to find the distance from that curve all the way down to that line. And what we saw is to find that distance, we would have to take the big curve minus the little curve in terms of x. So our big curve is the x squared plus 21, and we're going to subtract the little curve, which is the line -x minus 7. When we simplify this all down, we'll end up with x squared plus x plus 28. Now, this gives us everything we need to set up our definite integral. To find our exact area, it's going to be the integral of that height, x squared plus x plus 28. The delta x is our dx, and our limits of integration are going to be the ends of our interval from -7 to 10. Now you would just evaluate the integral. 1/3 x cubed plus 1/2 x squared plus 28x evaluated from -7 to 10. And if you do that, which you should try on your own, make sure that you get 949 1/6. Let's try that again. Now we want to find the area bound by the curve y equals 12 minus x squared and the line y equals x. We use our representative rectangle, and the base of that rectangle is a horizontal distance, so that will be delta x. The height of our rectangle is going to be that vertical distance in terms of x. So the big curve, 12 minus x squared, minus the little curve, x. So we'll end up with -x squared minus x plus 12. Now we can start setting up our definite integral, and that would be the -x squared minus x plus 12. The delta x is our dx, and our limits of integration are going to be the endpoints of our interval. That's one thing that we don't know now, because in the last example that was given to us. In this example, it's not. We need to go from this point of intersection to this point of intersection. That will define our limits of integration. To do that, we want to set these two equations equal to each other. So that would be when x is equal to 12 minus x squared. So I'll bring everything over to the left side. X squared plus x minus 12 equals 0. Factor it into x plus 4 and x minus 3. And we'll get that x is equal to negative 4 and x is equal to positive 3. We could find those y coordinates, which aren't very difficult in this case, because y is equal to x is one of the equations. That means that this would relate to the point negative 4, negative 4. And this one gives us the point 3, 3. Our two endpoints. 3, 3, negative 4, negative 4. Now, of course, when we're looking at our limits of integration, all we care about, since everything is written in terms of x, are those two x coordinates. So we're going to integrate this from negative 4 up to positive 3. So let's evaluate that integral. Negative 1/3 x cubed minus 1/2 x squared plus 12x. Evaluate it from negative 4 to 3. You do all the algebra on that, you should end up with 57 1/6. When we look at this last example, finding the total area of the regions bound by the two curves, we recognize that there are two regions that we're going to have to find the area for. That means that we're going to need to have two representative rectangles and two integrals, which means two sets of limits of integration. So first thing we should do is probably find all of those points of intersection. With an accurate graph, we could probably guess where our points of intersection are going to be, but to be certain, we need to take the two equations and set them equal to each other. So 2x cubed plus x squared plus 2 is equal to negative x squared plus 4x plus 2. Bring everything over to one side. That's going to get these 2's to cancel, but adding x squared to both sides leaves us with plus 2x squared here, and subtracting 4x gets us at 0 on the right side. Now we can factor out the common factor of 2x, being left with x squared plus x minus 2. Factoring that one into x plus 2, x minus 1 leaves us with 3 different x coordinates. X equals 0, x equals negative 2, and x equals 1. If you want to go a step further and find their corresponding y coordinates, the three results would be the 0, 2. From here, negative 2, negative 10. And our last point would be at 1, 5. Meaning, our 3 points here happen at negative 2, 0, and 1. Now, when we set up our representative rectangles, we recognize that we're dealing with two separate regions, so we need two separate representative rectangles. In the first region, I have this green rectangle. The base of that rectangle, since it's a horizontal distance, will be delta x. Now, when we want to find the height of this rectangle, remember to take the big curve minus the small curve. That's what's going to be very important. When we recognize what the big curve is, we kind of follow it to its equation, that being 2x cubed plus x squared plus 2. The smaller curve then is going to be negative x squared plus 4x plus 2. When we simplify everything, we'll have 2x cubed plus 2x squared minus 4x. And the 2 minus 2 will cancel. Now, when we look to the other representative rectangle that we have here, the base of this rectangle is also a change in x. But when we're looking towards the height of that rectangle, we recognize that the two functions got flipped around. Now the larger curve is the negative x squared plus 4x plus 2. And the smaller curve is the cubic 2x cubed plus x squared plus 2. So we go to simplifying it, and we recognize that we just switch the order of subtraction. So our difference is going to be the opposite of what was above. Now we have our two regions that we need to set up two definite integrals for. So our total area will be the area of the first region, which is 2x cubed plus 2x squared minus 4x dx. And that interval goes from that negative 2 to 0. The next area goes from 0 to 1. And it is the opposite function, the 2x cubed minus 2x squared plus 4x dx. If you calculate that on your own, you should simplify it down to 6 1/6 as a final answer.